Welcome. I want to talk a little bit more about Morse's theory on graphs, and I pretended that it only works for manifolds, but actually it works for rather general graphs. What you have is a function, if you have a function on vertices which has the property that it's locally injective and that the stable sphere is always a sphere in a graph theoretical case, or contractible, then we can talk about the Morse function. And there are different cases, right? You have either a regular point case when the stable sphere is contractible, or it is a critical point and then the Morse index is k if we have attached it to a k-1 sphere. So what we think about is the complex being built up, and I want to illustrate this with a specific graph, which we have the integers 1, 2, 3, 4, 5 and so on. So this defines a graph can attach an edge to two numbers if one divides the other. This is a very natural graph, and we will see it's very, very interesting because the topology of this graph, the geometry, when n becomes larger and larger, the growth rate of the Euler characteristic is actually equivalent to the Riemann hypothesis, the most important open problem in mathematics. Just quickly about the general setup. I've defined this already last time, right? We have different numbers which we can attach. Now we can attach the number of critical points, ck of index k, or we can also attach Betti numbers, bk, for a finite simple graph. We can attach Betti numbers, which are the kernels of these Hodge block matrices. It's defined for any graph. And fk, that's another thing. You can look at quantity, which is the number of complete subgraphs in a graph. And then we have this beautiful identity, which actually consists of two theorems. So there are two theorems actually involved here. The Euler characteristic can be defined like that, as the number of even-dimensional simplices minus the number of odd-dimensional simplices, but it's also the alternating sum of the Betti numbers. That's actually just very easy to show using the heat deformation flow. This is the Poincare-Hopf formula, which also is quite clear inductively. So the Euler characteristic can be written also as a sum of Poincare-Hopf indices of a function. These are functions for which the Poincare-Hopf index formula works. So locally injective is the only thing we need. But we have a little bit more structure here. There are spheres, so this means the Poincare-Hopf indices are either 1 or -1, depending on whether k is odd or even, and that's why we get this. This is actually an identity which holds in general. And if you just truncate it, if you just take the alternating sum until k and not the whole thing, then we get inequalities. These are called the strong Morse inequalities, one of the major theorems in Morse theory. And in the graph case, it's quite easy to show. What you do is inductively you see what happens when you attach a new vertex. Either it's a regular point and nothing happens, or nothing happens to the Betti numbers and nothing happens to the critical points, or you add a critical point, and then what you have you either close a sphere which is existing, or you open a new sphere. And if you close an old sphere, then bk-1 gets changed, decreased, or you add another bk. So this is, you just by induction add more and more of these cells. This is the Morse build-up of a graph. Not all graphs carry a Morse function. For example, cube graph has no Morse function, because you cannot even take one vertex away. The vertex, the unit sphere of this vertex, is a 3-point graph. That's not a sphere. For example, every barycentric refinement of a graph, here it's defined again, the barycentric refinement of a graph always admits Morse function, and the most important one is the dimension function. We start with counting with 2, and then we take the next number, which is 3. So they don't divide each other. They are both prime, so they are not connected with each other. But now comes 4. 4 is actually, when you add 4, you have a square. You have two primes are multiplied, so this is not square free. This is actually a homotopy extension. So what we have is kind of, if you look at that here, So this is just attaching the unit, the stable sphere is just a one-point graph which is contractible. So this is a homotopy step. Then we have 5, which is again prime. So that's a single vertex. And then we have the next number is already interesting, 6. So if you have 6, that's 2 times 3. That's attached to 2 and to 3. So let's do that. And actually these 2 points, 2 and 3, is a sphere. It's a zero-dimensional sphere. So we attach this to the zero-dimensional sphere. So let's just do that here. And so we attach 6 to the 2 and 3. That's now our graph built up until 6. 7 is again a prime, right? And then we have 8. 8 is again not square free, as we attach this to 4 and 2. So what we do is we attach it again to a complete subgraph of 2 elements, which is contractible, right? So we are doing this is a homotopy extension. That's not an interesting step. And now comes 9. Also, that's not an interesting step because we attach it just to 3. It's only attached to 3. It only divides 3. And the 10 is again interesting. 10, actually we attach again, what happens when you attach 10? You attach it to 2 and 5. So where is 2 and 5 here? So we have 2 and 5. I can attach this 10 here. And what happens if we attach it to a sphere, to a zero-dimensional sphere? What we have done, we have closed that sphere. So we have removed one of the Betty numbers. So whenever we add a prime, a new prime, you increase the zeroth Betty number because we increase the number of common connected components. And then, for example, if you take a new number which is attached to a sphere, then that sphere, that zero sphere, is closed, and so the zeroth Betty number is removed. So that's this case here. 11, this is again prime, a critical point, right? Because stable sphere is the empty graph. The empty graph is a -1 dimensional sphere, so that has the index 0. So that adds B0, adds 1 here, but it adds also Z0, the number of critical points of index 0. These are just these primes here. And then 12 is interesting. So what happens is 12 gets attached to, so actually it's maybe better here, 12 gets attached to 3, 6, 2, 4. But what this is a contractible space. So this is a contractible stable sphere. So that's a homotopy step. Adding 12 has nothing added, and we add 13, which is the next one. So it was alone. And then, and so on. We add more and more points. And you see 13 gets grabbed back to the main graph when we add 26. 26, it becomes more and more interesting. For example, when we add 30, this is a step where we close a one-dimensional sphere, right? We have this one-dimensional sphere, which is C6 here. This was, before 30 was there, this was an open sphere which carried a cohomology B1, which added 1 B1. And if we close that, the B1 gets removed. Here present, when we add 21, we actually close a one-dimensional sphere, which means we increase the Betty number by B1 by 1. So this happened before, like here, for example, when you added 15, we also closed the sphere. We closed the one-dimensional sphere. This sphere got removed when we had 30. 30 is 2 times 3 times 5. It's a product of 3 prime. That's the build-up, and you can now look at the Euler characteristic of this graph. How does the Euler characteristic grow? And that's very interesting because it's related to this is the Moebius mu function, which is -1 if there is not number of primes in the prime factorization. Different primes, it's 1 if there's an even number of primes in the prime factorization, they're all different. And if there's a square factor, then it's 0. So, and then because what happens is 1 is also included here. So mu1 is actually counted as 1. So you have to remove that, and because of the negative sign, you have a 1 minus mn. So 1 minus mn it follows from Poincare-Hopf, and it also follows from the fact that these are the Poincare-Hopf indices. The Morse assumption assured that 1 minus the Euler characteristic of the stable sphere, that's the Poincare-Hopf index, is equal to 1 or minus 1, depending on whether the sphere has Euler characteristic 0 or 2. When I wrote this in 2016, I was not aware of this paper of Bjoerner, Anders Bjoerner, who wrote already earlier on that, but used the language of simply sphere complexes. So let me say how I got to this. So I was thinking about number theory, but also thought about at that time about also barycentric refinements. So if you take the prime graph, the graph of all primes, things are connected with each other to the complete graph, and then you take the barycentric refinement. The barycentric refinement consists of all simplices as vertices. For example, a triangle here. So if you take a triangle 5, 11, and 13, then you can associate to this also the product of the numbers 5 times 11 times 13. So this number has these 3 prime factors, and you think about this number as a triangle in this prime graph, and which is a point in the barycentric refinement. And in the barycentric refinement, you attach 2 simplices if one is contained in the other, which means in the number theory that one is divides the other. So that's this counting graph here. You don't get numbers which have a square factor. For example, you don't get 12 or you don't get 9. So when you're building this up, these numbers are just not coming up. So I put them in another color, but it doesn't actually matter from a homotopy point of view, because whenever you add a number which has a square, what actually happens is this is just a homotopy step, because the sphere which you have is contractible. So we have f0 is equal to 90, f1 is equal to 20. Why is b1 equal to 1? Because we have just one cycle here. This is one hole here. And also here, of course, b0 is equal to 0, b1 is equal to 1. The number of critical points agree here in both cases. And maybe I should say something about the Riemann hypothesis. So that's a very long old story. It has been studied for a very, very long time, more than 100 years. And Mertens conjectured that this mn is growing like square root of n, smaller equal than the square root of n. And if you look at it numerically, it looks like a random process, and what happens is the square root of n, that's kind of the square root of n. Square root functions are really kind of what you probabilistically expect, is that's how it grows. More precisely, you expect it to grow like the square root of 2n log n. That's by the law of iterated log. So if these numbers would be random, and so most of the 0, 1, minus 1 sequences, which mean here the 0 appears just with a certain probability, so it doesn't really matter what happens. The 0, these are the cases where you just do homotopy steps. These happen with a fixed probability, 6 over pi squared. So you can explicitly get that probability, and but then so it's essentially just a random walk. So, but it's a specific sequence. It's not a random sequence. If you take a random sequence, then you have that a property, and so that makes sense. And so for almost all sequences, it's like this multiverse of, if you would consider that kind of as a probability space of mathematics. So when you take prime numbers randomly, you take maybe sets of which behave like prime numbers asymptotically, and you look what happens, then you expect this to be true in general, and especially the Riemann hypothesis should be holding for almost all. By the way, there's a nice book of teach marks about the Riemann zeta function from the 30s, which has this kind of statement as a theorem. This is equivalent to the Riemann hypothesis here. And it's pretty clear because you have the 1 over zeta. The original zeta function converges for s bigger than 1, and then the square root of n gets you half down, right? So when you look at so this is 1, and s equal to 1/2. So one believes all the zeros are on the critical line, but if that holds here, then the inverse zeta function is analytic until here. And then if it's analytic until here, then there are no roots here of the zeta function, and then by the functional equation there are also no roots on the other side, and so the Riemann hypothesis is shown. So that has been known, I think, already by Mertens, more than 100 years ago, or by Stieltjes or so. That this was a kind of a very, very early approach to the Riemann hypothesis. This mu n doesn't really behave randomly. I asked that 20 years ago, Andrew Orlitzko, who had kind of visited at that time the department, and I asked him about this, randomness, and he was actually the right person to ask, because in 1985, 37 years ago, he has proven with Murray Hill that this is false. Starts to fail maybe at 10 to the 65 or so. Can never reach that by a computer. Alan Turing didn't believe in the Riemann hypothesis. He was looking for counterexample. He was computing the first 1,000 roots of the zeta function. Pretty amazing at that time. He had only access to, say, Manchester Mark I computer and not the modern computers we have nowadays. But he was able to compute 1,000 roots, the first 1,000 roots of the Riemann set, and verify that it's on the critical line. Also this, if you look at this here, this conjecture, this has, of course, nobody has found anything here even for epsilon equal to 0, a counterexample with a O. But one doesn't know, for example, it could be that mn is smaller than 10 times the square root of n. Nobody believes that. I think what is the most common reasonable belief is that the Riemann hypothesis is true, and that actually the mu n behaves like a random number, and then the law of iterated logarithm, which is one of the basic pillars of probability theory, would apply, and you would actually get this. But this is not a random number, and it actually doesn't even behave randomly if you make statistical tests. Turing didn't believe in the Riemann hypothesis to be true, but nowadays I think most of the mathematicians believe the Riemann hypothesis is true. I personally don't believe. So if there's a kind of a thing, if there's not a reason for something to be true, it's false, and there's no reason why it is true, and no reason has emerged. It's kind of like Murphy's law, and it could fail after very, 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 for very, very large numbers only. So even that could fail for very, 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 very large numbers. So it appears that this is actually pretty good. And even that with the square root of n and the epsilon 0 and the constant here actually looks very good numerically, but these are just very small numbers. And this is not something where you can kind of just behave like a physicist and say, okay, these are the numbers we can access and we can experiment with. For every physicist, this is true. And but you also cannot go into kind of some multiverse thing where you say, okay, we assume that the kind of this number here is just one number of all possible numbers. For me, it was always a very kind of accessible approach to the Riemann hypothesis. Right? These numbers, number of whether an integer has an even number of prime factors or an odd number of prime factors. This is something which kind of behaves in a random way, and it's reasonable to believe that this is random, but this is not about belief, it is about proving things, and so this could well be wrong, and it could well be wrong just simply because there is no reason that it's right. Okay, that's it.